When patchers grow, dealing with the amount of patch cords as well as the available space becomes an important topic. This episode shows some helpful strategies. A typical approach to generating random behavior is predefining a set of possible values from which one is randomly chosen. The select object generates at the respective outlet a trigger which triggers the value connected to it. This all works fine, but imagine when working with 20 values and the amount of connections that would require. Often there are better approaches possible which reduce patch cord usage by many meters. In this case, a ZL lookup could be used as well. This makes it much simpler, clearer and easier to maintain. In this specific case, everything can even be realized with a single expression object. At some point, we may need user interface objects to represent a sequence of complex settings. An array of toggles, for instance, could become such a sequence. The toggle connects to a join object with the trigger attribute set to -1, which makes all inlets hot. In this way, all information is combined into a single list so that it can be processed elsewhere. Now imagine this needs to be extended to 16 toggles or even 32. Patching this is very time-consuming. But we have been introduced to an object earlier which could easily hold the same information, the matrix control object. Reduced to a single row, it looks like a set of toggles. A getRow command allows us to read the information. Since the amount of columns can be dynamically changed, extending this to 16 requires no additional patching. For obvious reasons, this is preferable over the toggles solution. The patterns generated by a logistic map that we saw in a previous episode is more interesting when played with multiple voices. First, a few improvements. The trigger object creates more clarity. The R value only is interesting in the range from 3 to 4. And instead of setting the initial state with a message, this can be done automatically when the R value is provided. The threshold is better set at around 2/3. When we want 2 of these, we can simply duplicate the patch. This patch is rather compact, so it looks fine, but as patches grow, this easily becomes unmanageable. Better would be to use a modular approach. With all objects selected that will become part of a module, the encapsulate command or Command-Shift-E puts everything in a box while keeping the connections. A double click shows us the content of this object. Automatically at the top inlets were created and at the bottom outlets. As a matter of fact, a single outlet would be sufficient when the result of makeNode is joined in a list. The object we see here is called a patcher, P, and can be given a name. An empty patcher has no inlets or outlets, but they can be created. For clarity, let's name this patcher so as to point out its function. Duplicating now is simple and doesn't require much space at all. Before testing, it would be good to change the sound of the percussive instrument of the second voice. Communicating with what is inside a patcher can also be done without patch cords. A send object can send data to corresponding receive objects indicated by the argument that has been specified. Any argument is fine, but it is advisable to use names that clearly explain their function. The node information can also be sent, leaving us with a patcher with a single inlet. The pitch of the second needs to be adjusted again. Instead of having to go inside the patcher to change the pitch, it would be much easier if it could be specified as an additional argument. Such a strategy can indeed be used. In this case, we need the patcher args object. This object, when triggered, reveals all the typed-in arguments, 2 in this case. The second one will become the pitch to be triggered. Now, making variations of the same principle becomes much easier, and it is more clear what is going on. Instead of manually triggering the patcher args object, reopening the patch after saving will trigger them as well. In an earlier episode, this patch showed how through the use of a number of ZL objects, a random pick based on a queue is created. This looks like an approach we can use more often in other patches. In such a case, the procedure is to first save the patch with a clear name and to create a new patch in the same location where we saved the other, and simply type the name of the patch in a new object. This shows that this is a valid approach. Although the randPick object does not exist, we can include it as a patcher that looks like an object. Such patchers are referred to as abstractions. It doesn't have any inlets or outlets, so that is something to take care of. Also, the option to provide arguments sounds like a good idea. In this case, the name of the abstraction will not be reported, only the arguments that follow after. The first will set the size, the second the amount of values to choose from. Testing this shows the value we expect to see. There exists a naming convention for abstractions like the one we have created. This convention is to start the name with a prefix that clearly points out the creator or an origin. In this case, the prefix RMM would make sense. Additionally, it is advisable to provide some explanation about what the abstraction does. That is good for ourselves and useful for others too. The tester requires its name to be updated, but then it will work fine. In the case of abstractions, a consideration is to keep them in a designated place where Max can find them. The Options menu shows file preferences which can be set to point to a specific folder. Everything listed here is searched when Max launches. This patch was used some episodes ago to show how to create chunks from a buffer. Here, the F objects that stored values for start and duration have been updated to expressions that include deviations of those two parameters. Such deviation makes it interesting to have 2 or even more versions running on equally so many channels. The task is then to create an abstraction that makes such approaches easy. Sends and receives will be used for all parameters. Additionally, a gate is implemented for turning on and off the playing of chunks. Turning on generates a trigger for the process to start. Next, everything that becomes the abstraction is cut and pasted into a new patcher file. An outlet is added and the patcher saved. The main patcher is stored in the same location. After this step, it will be possible to use the abstraction. Let's give this a try. Duplicating for the other channel now is easy. Another approach takes such patches and creates a polyphony of them. The poly object does just that, with an argument for the patch that needs to be loaded and an argument for the amount of voices. Although the object has an inlet, no outlet appears to be present. For this specific environment, we need to adjust the abstraction. The outlet no longer works. Instead, an out object needs to be used, in this case with a tilde. An argument indicates that this will be the first outlet. Now the poly object shows an outlet. Since there are two voices, a multiplication with 0.5 makes sense. At this point we hear 4 voices, 2 on the left and 2 on the right channel. Instead of having to deal with multiple files in a folder, Max provides the option to save a patch as a project. This creates a hierarchy of elements that are kept together so that it will always work. The Finder reveals that a structure of folder has been created that will be updated automatically when parts are added. Projects come with other options too, for instance to back up a project in an archive. In PD, subpatches are named PD. The inlets and outlets are there too, however, as regular objects. Sending and receiving works fine. For abstractions, the PD control object can be used to report arguments. And the clone object is similar to poly in Max, as it can instantiate multiple versions of the same patch.